So Matt is a professor at Stanford University. He's also the original and prototypical network economist. And he's done a lot of work in strategic issues in network formation. But I think today he's going to focus more on your village here.
Well, there'll be some village, yeah.
So one of the things he's going to allude to today is this beautiful data set that he and his collaborators have collected, where they went to 70 villages in India, and they got very detailed social interactions. And it's an excellent and outstanding data set.
Thanks, Ashish. So this is joint work with Arun and following up on the talk he gave earlier this morning. And I started with just a quote from Jacob Moreno and Helen Hall-Jennings, emphasizing the point that we're really interested in interdependencies in network formation, and that's an important part of social aspects, and we need to deal with that. And I don't know if people really know this, but I was just talking to Michael about this. Moreno actually was the first person to start doing social network analysis in a meaningful way, and was the first SUGM, what came from 1932. This is a mapping of interconnections, friendship networks in Columbia University, I think, and various halls. And he was interested in trying to figure out what the real halls should be. So he was doing sort of clustering before anyone was doing clustering. But that's fun tidbit of knowledge. But basically, the point here is that there's a lot of interconnections between these relationships. Interdependencies are essential, and we need estimable models to deal with these. And the kinds of questions that arise, are you more likely to link to friends of friends? Do relationships need to be embedded in certain structures to function? So when we actually look at things like favor exchange in some of the villages that Ashish was referring to, having friends in common becomes an important aspect of making sure that you actually abide by the kinds of agreements and the reciprocity that are expected under social norms. So there's reasons to believe that you need certain kinds of structures in order to make societies function. And do you want to link to others who are well connected? Is that something that's desirable to get information and so forth? So these kinds of things mean that there's going to be dependencies that we need somehow to take advantage of. And I'll talk about the data set that Ashish was referring to a little bit. So we basically have 75 different villages of data. This is a picture of village 26, and this is the kerosene rice network. And basically nodes here are households, and a link between them means that they share kerosene and rice between the households. And in particular, one thing that you notice here, there's an enormous amount of homophily. So these are color-coded by caste designation. And in particular, blue are what are called scheduled castes and scheduled tribes. So there's actually like 53 different castes in the villages. And this is just a broad cut in two. So scheduled castes and scheduled tribes are the affirmative action castes recognized by the Indian government. And then the red are general and otherwise backward castes. And one thing you begin to notice is that the frequency of links within is a little more than 10 times higher than the frequency of links across, and so that gives you an idea that there's substantial homophily here. We could begin to model this by a block model, but what we're interested in is understanding whether there's specific patterns to these kinds of links. And one question you might begin to, as a social scientist, we're interested in particular, which brings these link dependencies to the forefront, is when we look at people from different castes, are we more likely to see these kinds of relationships in situations where they're in isolation, or would you also see them when they have friends in common? Okay, so would there be social pressures that would mean that you're more likely to do this if nobody else is witnessing it, or if it's not conspicuous, than if you have this embedded in a triangle? And so what we'd like to do is have models that begin to allow us to answer this kind of question. And a straight block model won't give us the ability to answer that question directly. Okay. So what we're going to do is, starting from social scientific questions, we want models that allow us to test for specific theories of graph formation. We want those to be covariate-based, subgraph-based. And another thing we want models that can predict out of sample. And so the models should also be ones, ultimately, why would you be interested in these kinds of things? You're going to be interested because you might want to be instituting a policy that increases interaction and sharing across groups or information transmission or something. And if you want to do that, then you want to be able to understand what's making the network look like it does and how would you change that. And so you need models that you can begin to figure out which parameters you might affect and how that might change the network structures. So you need generative models that you can go and do counterfactual kinds of exercises with. Okay, so that's sort of just a big picture of what we're after, and then this will bring us back to the models that Arun was talking about earlier this morning. Okay, so what we're going to look at is a class of models that we've called subgraph generation models, where effectively what we think of as the building block is not the network itself, but the building blocks are just formations of different subgraph structures, and those subgraph structures might serve specific social goals or aims. They might be beneficial for certain reasons, and those things are going to be the building blocks. So we'll just work directly with those things as the statistics, and the graph is sort of an incidental thing which is generated. So people are forming links, triangles, other kinds of things, isolates, and the networks are basically going to be a byproduct. Okay. So let me just review in case, people, things go by quickly in 20-minute talks, so I just want to make sure that we understand exactly what these subgraph generation models look like, and then I'll apply some of them to the Indian data. So nature, or people in these cases, are going to be forming different kinds of subgraphs. So there might be some subgraph of type J, and there's going to be a statistic which just counts in our given population that we have observed how many of those things did we actually see. Okay? And these things may intersect and overlap, and we observe this resulting network, and we try and infer the probabilities of these different objects being formed. And then those things will inform us, allow us to test hypotheses about the cross-cast kinds of things and so forth.
So when you say the network's a byproduct, and what you mean is that at the end of the day you're going to be interested in making claims about these very local interactions and not...
Exactly. So we're interested in understanding, we're interested in so we're going to be interested basically in the local structures that emerge and trying to understand, is it more likely that people are going to be embedded in these triangles or links and so forth. And so we want models that allow us to test those kinds of things. They'll generate networks for us. And so we can talk about general network properties, and they'll generate things where we can do path length calculations, giant component calculations, and so forth. But those are all going to be incidentals and not the primitives that we'll work with. And so we'll still be interested. It doesn't mean to say we're not interested in the network structures generally. It just means that those are going to be incidental to the structures, not the generative underlying pieces. Okay, so just as an example, just to bring back, to reiterate what Arun talked about. So we have these nodes. People can meet in triples, and they meet randomly, and they decide whether to form these relationships. Some triangles form. People can also form bilateral relationships. Some of those emerge. And then, the part in terms of estimation of the model is these things can confound each other because you can get some overlaps and so forth. And so then the estimation problem is just inferring what these different probabilities were from the actual data. And as Arun pointed out, when things are sparse enough, this is going to happen relatively infrequently. And so doing direct counts of the actual objects of triangles and links and so forth allows you then to go back and really understand and recover what the relative frequencies and probabilities are. Okay, so that's the basic idea of these kinds of models. And so what we see is the resulting network, and we don't know that this triangle was actually generated actually as a link and edges of other triangles, but that happens relatively infrequently, and so the estimation can go through. Yeah.
So you're probably doing this like probabilistically on nodes, but is there a way in which we could think about it agentially on nodes, in the sense that they have an awareness of what ties they're making?
Exactly. So I'm going to come to that, and effectively what's going to happen is these probabilities are going to come from the choices of the individuals. And so one thing that we want to understand is, do we feel this social pressure? So is there a different benefit that I get from forming a link across castes if there's somebody else sees me than if I don't?
Right.
And so we'll...
I guess to that, well, you'll probably guess, but my question on that point is, how much is in their head? Like, so if someone forms a tie to them, I might feel like passive about that. Or am I aware that they have a tie to someone else?
Yeah,
and should
yeah.
I consider that?
Yeah, so I guess in general, as social scientists, we don't. Well, we some people do look in people's heads. There are neuroscientists who are literally trying to figure out exactly what's going on in people's heads. But at this level, we're not going to be able to look in people's heads. What we're going to be able to do is as if kinds of. So we'll be able to calculate. Look, if we infer that people are doing things that are beneficial for them and tend not to do things that aren't beneficial, then we can recover some preference relationships from the data. But whether or not that's actually what people thought of explicitly, whether they were calculating in these things. I think the story in terms of strategic models is more an as-if story in the sense that over time, if there's relationships that somehow don't feel good to me, I drop them, and if there are ones that seem beneficial, I add them. And whether people are calculating in a cold, hard way, it's not so obvious.
Yeah. I mean, the only reason it becomes relevant is when we start to think about functionality of a network being created and how much of that functionality people are aware of as they're creating it.
Right. Yeah. And here they'll have to be able to assess local patterns and benefits and costs of those things. Okay. So one thing just to start out, these subgraph generation models we can view as statistical exponential random graph models, a point that Arun pointed to earlier, and that turns out to be useful. So one is just a very easy theorem on these subgraph generation models. So if you work in a world where the world throws down different types of objects, subgraphs, and possibly with covariates and so forth, and what you do is now you keep track of all the statistics and then a bunch of parameters on those statistics. If you look at that model and look at the probability that a given type of statistic or subgraph is generated, and you did a fairly naive calculation, which is you just set the parameter, you set a parameter equal to the log odds ratio of that object being present to not being present, and you counted possible statistics by looking at how many you got out of how many were possible, and just did a choose operation, so a simple binomial calculation, then the probability of the actual statistics coming out has this exponential random graph model formulation. So the exponential family actually is a representation of this if you can observe the true counts of all these subgraphs. Okay? So the problem is that link, we're going to have some bias in the sense that you're actually not going to observe exactly how many links were generated and how many triangles. You're going to have to estimate that. But if you could see exactly what those are, then it would fit exactly into the exponential family. And why is the exponential family so nice? It's probably one of the most studied sets of distributions. We know a lot of things about it, the convergence properties, all kinds of things are very easy to work with here. And so this gives us some nice mathematics behind these things, and then you can prove things about these kinds of this family. You can also prove them directly using different binomial calculations. Okay, so that's just sort of so there's a bunch of theorems we have in the paper about the relationship between these different kinds of models. Okay, so I want to do two illustrations of these things. So first of all, what's the useful of these things, and what do they add beyond block models to the data? And then what can we use in terms of preference-based models and strategic models, and how can they help us out? Okay, so what we're going to do is use these data from the 75 Indian villages. You can find these via my website. You can find them via Arun's website. So the data are we have 75 different villages where we went in and basically now we have pretty much a census of all the network. We have 13 different types of networks: borrowing and lending kerosene, rice, money, who do you go to for advice, who comes to visit your house. There's all kinds of different relationships. So there's lots of data there. And what we're going to do is let's estimate a model and then use it to generate networks. Okay, so this is just a question of, suppose we used a block model and generate networks back. Do they look like the real networks? Suppose we use one of these subgraph generation models, estimate it, then use it to generate networks and see what we get back. Okay. Now the pure exponential random graph models you can't do directly because you can't estimate them, as Arun pointed out this morning, but you can estimate this family of them using the subgraphs directly. Okay, so what we want to do is how well did the model recreate the networks? but especially on non-modeled characteristics, right? So obviously, if you're fitting these things directly to certain characteristics, they should do fairly well. But the question is, do they get other aspects of the networks that we didn't put into the models? Do they answer those fairly well? Okay, so what we're going to do is we're going to estimate a subgraph generation model on covariates, allowing for triangle counts. And then we'll also do sort of a standard link-based block model based on the covariates. So here are the covariates. The main covariates we're going to use are GPS data and CAST data. But you can put in a lot more, and basically the pictures will look pretty much the same. Okay, so what do we do? So here's the actual data, a bunch of different things that we might be interested in the network. So how many triangles are there? How many unsupported links, so links that aren't in triangles? What's the average degree? How many isolated nodes are there? What's the coefficient, clustering coefficient? What's the fraction of links, nodes in the giant component? What's the first eigenvalue of the adjacency matrix? What's the second eigenvalue of the stochasticized adjacency matrix? This is a measure of the best cut in the graph, or a homophily cut. What's the average path length, and so forth. Okay, so you've got a whole series of different things. And basically, what we're doing is, if you look at fitting a link-based block model, what it's going to be matching on is really degree, right? So it should nail degree fairly well, because you're trying to get link frequencies. And so it's got to hit that right on, and indeed, it's going to match the data exactly on average degree. Now, the subgraph generation model, what it's doing is basically counting links and triangles. It'll get triangles and unsupported links well. It overestimates degree a little bit. Both of them do pretty poorly at figuring out how many isolates there should be. So what happens is, in these kinds of villages, you tend to have some people who are just asocial for whatever reason, for actually person reasons, aren't interacting with other individuals. And so if you just fit the model directly, you don't pick up enough of them. And so what you can do is you can throw in isolates into the subgraph model too. And if you do that, you come a little closer on that. But here, you pick up pretty well these kinds of statistics. But then the question is, how well do you do on the other things? And the kinds of things that you're going to pick up, not surprisingly, clustering is going to be a lot better under these class of models, because you're putting in triangles explicitly, so you're going to match clustering much better. And then when you go into fractions of the giant component, or first eigenvalue, second eigenvalue, and so forth, you basically end up doing better in these cases at matching some of the things. And I can just sort of go through. So here's the actual data is in gray here. This is the CDF of the degree distribution, sort of averaged across all the villages. And then what you can get is, if you do the subgraph generation model, you get this blue line, which actually doesn't match the average as well, but matches the CDF more closely than what you actually get out of the block model.
So you have, you said 70 or something villages.
Yeah.
And they all have roughly the same number of nodes you put upward, or 100 or something?
There's roughly 200 households per village, yeah.
The villages talk to each other, or each one's...
No, they're fairly separate. So they're about 40 kilometers apart mostly. So part of the reason we went to these villages, they're very rural. It was part of a microfinance diffusion experiment that we were involved with. So these are fairly isolated rural villages. There's some occasional intermarriages between these, but relatively little interaction among the villages. So you can really treat these as more or less 75 different populations.
How did you choose the number of blocks? You said block models.
Yeah. So the block here is not latent block models, but this is explicit blocks based on the covariates. So what we do is we just look at observable covariates and then fit the. So this is more the sociology term of block model that has become used in statistics. So it's not latent space, but it's really the original block models going back to the 1960s from the sociology literature. So here we're fitting it based on observed characteristics. But we have a lot of observed characteristics. So you can see pretty much, we know that people's age, profession, their caste, their some measures of wealth level, how many people are in the households, GPS data. So we have a lot of information about the individuals to work on.
But if you just do parameter counts in the two models, how do they?
So basically what we do in the subgraph generation model is we're adding triangles. So the parameter count goes up because we're adding triangles, yes.
Between the two models, how many degrees of freedom do you have?
So let's see, we have, let me get it exactly. So we have, so the versions in these graph are 4 for the block model, and 6 for the SUGM. Yeah. So they're both relatively small compared to the number of villages. When you see the clustering, then obviously the subgraph generation model is going to match clustering distributions much better because the block model just doesn't produce triangles, right? So it's rare that you get triangles unless even when you're generating fairly small blocks. So if you begin to look at, here's the clustering, 75 village worth. And what we do is we also have an algorithm for estimating exactly how many overlaps there might be. So the theorem sort of says asymptotically you don't have to worry about overlap. In finite samples you can have overlap probabilities. And so you can do a finite set correction for that. We have an algorithm for doing that. And that puts you a little closer. So here's where the subgraph generation models and the block models obviously miss the clustering. If you begin to look at the first eigenvalues, these models recreate the first eigenvalues better than you tend to get from block models. If you look at the second eigenvalue of the stochasticized matrix, all the data tends to be, the numbers are extremely high. So these are very, very segregated networks. So when you look at these villages, the cast really cuts across these villages. And so you tend to have really high second eigenvalues of this matrix. So that means that that there's going to be a cut almost where you can divide things in with extremely low connectivity across. And here the block models just don't pick that up. Okay, so one thing is isolates it's not doing so well. If you throw in isolates, you do better. So basically, what that just shows is adding these extra subgraph structures allows us to recreate structures of the network with a fairly simple model. So we're just throwing in the triangles, and yet that helps us pick up a lot of other things that were going on in the network in terms of observation.
Peter's question, if it's not capturing the clustering structure, you want a latent block model, or you want a mixed effects block model where you have some covariate-based blocks and some latent blocks.
Right. So here we're pretty sure that the reason it's not picking up the clustering is not because there's latent things that are going on, but because it's explicitly not accounting for the dependency. Right. So the block model there's a dependency that's going on that's at more than the block level, and I think one of the stories that the dependency is going on, there's sort of two stories that they go on in these. One is that actually having friends in common helps enforce behavior. So if I'm borrowing and lending, having a friend in common actually helps me execute that. And so there's going to be a tendency to try and complete 2 stars. So it's saying that there's actually a reason for having those things that's not going to be picked up by a block model.
But a latent block model would want to put them in the same block.
Right. So put them in the same block. And what I'm saying is even if you put them in the same block, there's going to be more that once I put in, so generally if I put people in the same block, let's suppose that there's a block here. And I still think that within block, links are formed independently. So if 2 people are sitting in a situation like this, and there's another 2 people that are sitting in a situation like this, the probability of this is going to be the same as the probability of this link within a block. Right? Once I've uncovered the latent block as well. And the claim I'm making is that you're going to tend to see them with higher probability conditional on the structure, even conditional on the block structure. So given all the characteristics that are determining these things, you're still going to see these extra correlations, and they're there for a particular reason, which is that helps people actually transact if they have people in common. That's the basic point. Okay, so let's talk quickly at the end now about these caste relationships. Are they more likely to occur in private with no friends in common, or do you see them with the same frequency across embedded relationships? And this will get to what Damon's question was. So, we'll start to put preferences on these individuals and explicitly model why they might be forming links. And so let's think of a situation now. We've got these characteristics of a given individual, and the individual is going to get some benefit from having, say, a link. But if they have characteristics xi and the person they're linking to has characteristics xj. So there's some benefit of actually having this transaction. So this is somebody else who has, similar needs for kerosene. I'm going to be able to borrow and lend kerosene. That's worth a certain amount to me. If they're very different from me, maybe I don't have the same value and so forth. So there's actually a value which depends explicitly on this. Okay, and there's some distribution of the error term here. And what we're going to do is then the probability that a link is going to form is going to be proportional to the distribution. So if I'm looking at this error term, as long as the error term is less, actually there should be a minus here, but so I'm going to look at the value of the actual utility to one person, the value of the utility to another person. I perturb those utilities, and the probability that a link forms is going to be the probability that the first person finds it attractive times the probability that the second person finds it attractive, right? So we only form these if we both find the relationship attractive. It's a mutual consent situation. Okay. When we go to a triangle, then we're going to have 3 people involved, and so you're going to have basically a cube of the probabilities that they're each going to find it attractive, right? So it's going to scale slightly differently, and that's going to give you a slightly different probability of forming triangles than forming links. So links take consent of 2 people, triangles take consent of 3 people, so you're going to have to, the error term is going to be cubed here instead of squared. Okay? So now if we have a null hypothesis that the probability that I prefer a cross-cast triad to the probability I prefer a within-cast triad is the same as the probability that I prefer a cross-cast link than a within-cast link, right? So what we're doing is now just testing that hypothesis that I somehow feel more conspicuous. So the alternative hypothesis is that this one is going to be less, right? So I'm going to feel less likely to want to form these things if I'm involved in a situation where other people are present. But now what we have to do is control for the fact that these things involve 3 consents. Otherwise, that's going to drive this naturally down. So we want to control for the fact that that's going to be less prevalent just because there's 3 people involved than 2. Okay. So what this thing looks like is the cube of this probability that I find it beneficial, and this is the square. And so what we're going to end up with is the probability that you prefer to form cross-cast triads is going to look like the frequency counts to the third, and this one will look like to the half. Okay, and that corrects for the bias that you're naturally going to find. Otherwise, it would look like that the triangles are less prevalent already. Okay, so then if you plot the 75 villages. And here basically on the 45-degree line, if we look at the relative link frequencies down here from a crosscast compared to same, and then do the triangles here, they would be lining up on the 45-degree line if you ended up with it under the null hypothesis, and under the alternative hypothesis they should be below. And indeed, the fraction of them are below. If you do a simple test on this, at the 99.9% level, that you reject the null. And in particular, what's interesting is, so what we did here is divided the villages into 2 categories. Those where the villages are fairly balanced in terms of caste. So if you look at the upper castes and the lower castes, there's a fairly even balance. And then the light blue ones are ones where you have fairly balanced ones, and the red ones are ones where the smaller caste is actually a fairly small minority. So what we do is we look at the ratio of the bigger caste to the smaller caste, and then cut that at the median. And the light blue ones are ones where you have a fairly balanced ratio, and the red ones are where you have an imbalanced ratio. And the more balanced the ratio, the more segmented the societies become, and the more you see that these triangles are less prevalent compared to the links. Whereas if you look at the situation where you've got the fairly small minorities, they integrate better. And that's something you find in homophily fairly generally when you look across things. You see things segment much more when you've got even-sized groups than when you have lopsided-sized groups. Okay, so we reject the null hypothesis based on the model. People show us statistically significantly stronger preference. I mean, obviously this is all model inference. So let me just sort of summarize main points to take away from this then. So the exponential random graph models, as Arun alluded to this morning, face estimation challenges, and there's no general results on consistency. The block models are quite useful in terms of estimation, but they miss dependencies that are needed to test some particular social theories, where we explicitly are thinking that people are conditioning on observable traits and are forming subgraphs based on those traits. And what we're doing is working with statistics or subgraphs rather than networks. That simplifies things substantially. So these classes of models are estimable and have these dependencies in them. And then we get consistency, fast estimation. And then what you can do is you can actually use these things to generate networks, to look with these, test the hypotheses, and then do alternative kinds of things as well. So there's a bunch of stuff in the paper that we didn't talk about here. You can do multiplexing. Are we more likely to borrow and lend money with each other if we do kerosene and so forth? So there's a lot of that in there too. So I should stop.